So the first part here of diving into vision is to focus on the sensation part. So how do we get the information into our brains, transduce it into action potentials? And this is going to be all about light. Okay, the next slide is going to walk you through the visual spectrum of light that we can see, and it's a video from your textbook. We're just going to let that play, and then I'll catch up with you on the slide that follows.
The visual system transduces two features of the light wave itself, the wavelength and intensity. The wavelength is the distance between successive light waves. The distance from wave peak to wave peak is measured in units, called nanometers, nm, which are 1/1000th of a meter. If light waves are very close together, in the 400 nanometer range, we perceive the color violet. And if the waves are far apart in the 750 nanometer range, we perceive red. And of course, wavelengths in between these two extremes allow us to perceive the range of other colors within the visible spectrum, as you can see here. Humans are able to visually detect only light waves within the visible spectrum, but we can feel the effects of ultraviolet rays, which have a wavelength of less than 400 nanometers, on our skin as sunburn. Rattlesnakes can see light in the infrared range, which is greater than 700 nanometers, helping them to identify prey. The intensity of the light waves is transduced by the visual system as brightness information. The higher the intensity of the waves, the brighter the light is perceived to be. Of course, we perceive much more than color and brightness. Complex features of our visual world are processed by the brain, not the eye.
So that light from the external world, or at least the specific band of light that we can sense and perceive eventually, is all going to have to make its way through our sensory organs, which of course are the eye, right? And it's important to remember that with vision, everything is coming into the eye. We're not sending anything out in the world. We're just moving our head and our eyes around, and light is going to make its way into our eyes. So the only way to see something is to have light come through the eyes and to make it to the back of the eye to a place called the retina. Now there's a image here in your book that you should study. It's here on the slides as well. You should be able to label the parts of the eye, at least the ones that are highlighted here. And we're going to walk through some of the most important ones in just a second in terms of what they do. Just keep in mind the kind of order of this process where something from the outside world is going to project light bouncing off of it through the eye. It's going to go first through the cornea, which is here. And it's going to make its way through the pupil, which is surrounded by the iris. It's going to be bent by this thing called the lens, and then the light is going to make its way back to the back of the eye at the retina. There will be an optic nerve at the very back. That's going to be the nerve that sends the signal to your brain. Cool. So let's walk through that. We'll come back to this image in a second. So first part of the process, right? So the light's going to bounce off of something, come toward our eye, and the light needs to get past two things. Number one, your eyelids, of course, right? So your eyelids, of course, are there to protect and clean the eye, so you can blink and get stuff off of your eye. But they can, of course, also block light from entering, right? So light has to get past your eyelids, otherwise you can't see. The eyelids aren't technically part of the eye. As long as you've got your eyes open, then the light's first going to hit the cornea, right? So the very first layer of the eye is the cornea. It's a clear protective layer. It doesn't have any physiology to it, so it doesn't have any it doesn't change shape or do anything. It's just a layer that protects the eye. And then it does do some focusing of the light because it's this clear layer that the light goes through. So the light is focused toward the center just a little bit, but it doesn't adjust. Okay, so it doesn't change shape to adjust the light in different ways depending on where it's coming from or anything like that. So it's a passive filter. You can get LASIK surgery if you've ever known someone who's gotten LASIK or done it yourself, or something similar to that. And this will actually shave off or change the shape of the cornea so that the light will get bent differently at this very first stage. Okay. So if I'm not bending the light properly, I can actually change the shape of my cornea and it'll bend it passively a little bit differently. Okay, cool. So there's the cornea, the very first layer of the eye. All light has to go through the cornea. If the light gets through the cornea and gets bent a little bit, then you're going to then encounter the pupil and the iris. The iris, of course, is the pigmented area around the pupil, comes in a variety of different colors. Um, the iris is going to change shape, sort of expanding or contracting, so that then the pupil is going to change in size. Now, one thing to keep in mind is that the pupil is nothing. So the pupil is just a hole, and it's surrounded by the iris. So when we say that your pupil dilates or your pupil constricts, right? What we're really saying is that the iris is changing, right? Because the pupil is just a hole, right? So it's the iris that's actually regulating the pupil size, and the iris is going to allow that pupil to dilate, make a bigger hole, or constrict, make a smaller hole, to let in more or less light. And what it's doing basically is trying to get an optimal amount of light into your eye, because it's hard to see with too much light. If you've ever seen something like blown out or you've stared directly at the sun, right? And it's hard to see with too little light. Turn off the lights and see how that goes, right? So your pupil size is being changed by the iris to let in hopefully the optimal amount of light depending on your situation. So if you're in a dark room, the pupils dilate, we let in more light. Cool. So this is the pupil and the iris. The light's going to go through the pupil, but it's going to be regulated by the iris. The next step, so the light makes it through the cornea, it then makes it through the pupil with the size regulated by the iris to let more or less of it in. The next step is to hit this thing called the lens. And this is like the lens of a camera, right? That's going to then focus light to get it in focus, right? And it's focusing the lights that's coming in so that it can be sent to specific parts of the retina in the back of the eye. Now the lens, unlike the cornea, does adjust. Okay, so the lens changes shape. It gets thicker or thinner depending on where the light's coming from. And there are these muscles called the ciliary muscles that do that, the pull or release to make the lens thinner, like pulling it, tightening it together and smishing it, or releasing to allow it to be thicker. This focus process has a term, and that's called accommodation. So our lens accommodates the light coming in. Like, here are your accommodations, sir, right? So the light comes in, the lens accommodates it, either thicker or thinner, to let the light in and bend it the right amount to get to the back of your eye. Now, you might be aware that this doesn't always go well, right? If you have glasses or contacts like me, you might know that the lens doesn't always accommodate perfectly, and so it's bending the light and it's not getting to the center of your eye properly. Maybe it's bending it too much, so it's focusing just a little too early, or maybe it's not bending enough, so it's not quite getting to the center as well as it can. Okay, so you might get nearsightedness or farsightedness based on that. You might also know that that eyesight gets worse over time, particularly close-up eyesight. And what's going on there is that these ciliary muscles are getting weaker over time, and so you can't bend the light as much, or you can't, you can't pull the lens as much, and so over time we get this age-related farsightedness. Okay, it's just a natural thing. Well, those muscles weaken just like any other muscles in your body. Okay, so we have a lens that's adjusted by the ciliary muscles to bend the light properly to the retina. Sometimes this does that bending, that adjustment is called accommodation. Sometimes it doesn't always work properly, so we might need glasses. And sometimes this can decline with age, and that's called age-related farsightedness or presbyopia. Coming back to our image of the eye, we've walked through this process now, right? So an image of a flower here is going to get projected or bounced to the eye. It's going to go first through the cornea, assuming your eyelids are open. Then it's next going to go through the pupil, which is surrounded by the iris. The iris is going to change shape to let in more or less of that light. It's then going to go through the lens. The lens is adjusted or accommodated by ciliary muscles here, right? It's then going to change shape to project the light properly to the back of the eye. This area here called the retina. Okay, so it's going to come down here. It's actually going to be upside down at the retina to the back of the eye. Okay, and we'll talk about how that works specifically, what's going on at the center of the eye called the fovea, and the existence of something called the blind spot. We'll talk about that in the next video.